Okay, let me start by welcoming all of you. Good morning, good afternoon to folks joining in from the US. Good evening to the folks joining in from Europe and Asia. Okay, so while we have a few more people joining in, let me take this moment to share a few housekeeping rules. Okay, this webinar is a 1 hour session and we will have our speakers, Ayushman and Siva, who will present for the first 35 to 40 minutes. The second part of the session will be dedicated for answering any questions, thoughts, feedback, or doubts that you have. And in the final 5 minutes will be left for some closing comments. Also, on the bottom right side of the window, you will find a Q&A box wherein you can drop your questions. And towards the end of the session, our speakers will take those questions up depending on the time that's left. One more thing, the recording of this webinar will be made available to each one of you in your inbox after the session. Am I clear about those rules? Yeah, okay. So let's get started. Right. So first of all, I want to thank all of you for taking this time to join us today, and we look forward to have an enriching session for all of us. Just to talk a little bit about the history of this webinar series, we started off in the month of March 2022, and this series is known as the Cut the Clutter series, and this being our third episode. So here our speakers would talk about their experiences with experimentation framework. Let me introduce our speakers for today. Our first speaker, Ayushman Mathur. Hi, Ayush. Ayushman is part of the leadership team at FaxPan, wherein he manages client relationships while also working with cross-functional teams in building end-to-end analytical solutions across industries and functions. He's an MBA focused in product management and business analytics from University of California, Davis Graduate School of Management. Besides, he's an experienced professional in big data, analytics, artificial intelligence, and engineering space. Ayush, did I miss out on anything?
No, I think that was very kind. Thank you.
Thank you. Our co-speaker, Siva Sankar, works for FaxPan as an associate analytics manager. He works with the product leadership of a prominent e-commerce firm to enhance the products and features for an excellent user experience through product performance analytics. Also, he has worked across different areas of product development and specializes in product analytics and experimentation methodologies. He graduated from Arizona State University with an MBA and MS in business analytics. So hi, Siva. Welcome.
Yeah. Thanks, Parul.
Okay. So now that I'm done with the introduction of both our speakers for today, Ayushman, the floor is all yours. Thank you.
All right, thanks, Parul. Once again, welcome everyone. It's great to be here today with all of you and talk about experimentation. Something that we do a lot of as an organization that works with multiple clients across a lot of different industries. With that said, our guiding principle or our guiding objective today was for our audiences to truly walk away with a good understanding of all the options on the table, when it comes to experimentation, and what are some of the merits and demerits of each sort of available option that we have. Our hope is, that there is something here to learn for everyone, wherever you may be on the journey of, building experimentation muscle in your respective organizations. So with that said, the agenda today is laid out in the following way, where we start by introducing some thoughts around causal inference, from where we move on to talking about Frequentist, Bayesian, and Quasi experimental methods. And we'll wrap it up with an example of a decision-making framework, to select the best experiment for your particular use case within your organizations. And as Parul mentioned, if you have any questions along the webinar, just feel free to submit those questions on the portal, and we'll come around to addressing them towards the end of the session here. Perfect.
Okay, all right. In the first section, we are going to cover the basics of experimentation and a fundamental concept that underpins the need for experimentation. Let's look at a live scenario here. What you see here on the screen is a snapshot from the sign-up page of a credit card that's offered by a major credit card company in the US. They're offering 120,000 points as a joining bonus if you sign up for the card and fulfill certain conditions here. Now, they also have another variation of the same page for the same product, wherein they are offering 150,000 points instead of 120,000 points in the first version. Now, why will a company have two different versions for the same product and offer different points over here? Well, you don't get brownie points for guessing the right answer in an experimentation webinar. Yes, they are running an experimentation to understand the customer behavior based on the points that they are offering to customers. They are potentially testing the hypothesis that when they offer higher rewards, more applications are submitted for this card. This is not just one example in the market. This is just one example in the market. But if you are a customer that uses typical social media or an e-commerce site in a day, you would have probably been part of 30 to 40 experiments by now without you even realizing that you are part of the experiment. If the experiment setup has been made in such a way that you know that, then it beats the purpose of experimentation. Probably you will see a poll on your screen by now. Yes, the poll is here. Let's take a few seconds to answer this question. In 2013, eBay spent around $50 million on paid search ads. What do you think was their actual return from those search ads? For reference, generally when companies spend money on search ads, they can expect between 5 to 8 times return in revenue for the amount they spend. It's based on the products that they sell, but it's a typical range to help you out here. Okay. I hope there are enough responses. And let's look at who got this right over here. Okay, 43% says 500 million, 30% on 100 million, 11% 50 million, 14% less than 1 million. Okay, when eBay spent $50 million in 2013, they saw higher revenue coming in from those that clicked on those search ads. But it was just a mere correlation, which means that more amount spent in the marketing budget, and more revenue earned from those that clicked on the site. But they were doubtful of that and brought in researchers from University of California and University of Berkeley to understand the actual impact that was created by those search ads. Finally, they found out that the $50 million that they spent on the search ads wasn't useful at all. They did not bring in any incremental revenue to them. And they took a bold decision to stop buying search ads for prominent branded search terms on the search engine. Probably in the last 8 to 9 years, eBay would have saved more than $1 billion in just the search ad in just the search ad cost over these years. To understand this concept, let's look at two terminologies that are part of experimentation realm here: correlation and causation. Probably you would have heard about this, but let's revisit that. Correlation just says that two variables move together. It's like there is an increase in marketing budget and there is an increase in the revenue that we earn. It doesn't explicitly say that there is a cause and effect relationship between these two terms. It doesn't effectively mean that by increasing the marketing budget, we increase the sales. It just says that both were moving in the same direction. On the other hand, causation explains the cause and effect relationship between two variables. It's a way that establishes the impact created by one intervention or a change on another variable that we are measuring over here. Concept-wise, this might look like a simple one, but this is the most most of the business decisions that are made with mistakes are because of the misconceptions around correlation and causation. There is a coherent cognitive bias in the decision-making world and also in the environment that people often confuse correlation as causation, and they take big decisions which compound over years and won't produce results or even move in the negative direction. In the eBay example, if they have not realized that they have spent, they are spending on search ads without getting any results, they would have spent more than $1 billion by now, and they wouldn't even have realized that the $1 billion they spent would have made revenue to them. So correlations are kind of, using correlation to make decision is very, very dangerous in the business world. There is another afterthought that having more data will help in identifying causation and filtering it from the correlation, but that's also not a well-known factor, in that when you have more data, you are going to have more correlation, but you won't know which caused what, or you won't be able to estimate which cause created the effect that we are looking at. So identifying and ensuring causation is very important in the business world. And the process that we use to map the causation is called causal inference. There are many methods that companies and organizations use to identify causal inference, but the most efficient one that's used in the business world is experimentation. When we use causal inference, we eliminate prediction that's given by correlation, and we use more of a prominent decision making. In the randomized control experiments that we generally use, that's a proven and powerful scientific method to establish the effect of the intervention or the change that we are bringing in on the outcome variable. For those that are new to experiment, let's walk through a typical experimentation process here. Disclaimer: this is going to be a very simplified version of experimentation. There are many constraints and exceptions to this rule, so don't take this as the ultimate of experimentation. This is just for context setting. In an experimentation, we generally test a hypothesis, and once we decide the hypothesis that will help us in understanding the effect of intervention, we decide on the audience that we are going to test the intervention with, and we split the audience into two groups. One is the control group, and the other is the treatment group. The control group is the one that won't receive the intervention. The treatment group is the one that will receive the intervention that we are planning to roll out. We observe and we split these two by randomization, so that we don't introduce any bias in the group split. Otherwise, that bias will alter our effect estimation. Once we introduce the intervention, we observe the performance of both the groups over a period of time, and the net difference between the performance of these two groups is the one that is attributed to the effect of intervention here. If you look at the graph to the right, the blue line is the one that shows the behavior of the control group before and after we introduce the intervention. The treatment group, or the one that received the intervention, that behaved similar to the control group before the intervention, but after we introduced the intervention, that started behaving in a different way. And the difference between these two is attributed to the impact of the intervention. It's not just that the estimating the impact is important, but we also need to say that the impact that we estimated is true to what we are verifying at a very high confidence. And for that, we use statistical methods to understand the significance of the results that we are making. If we don't care for statistical significance, the impact that we estimated will be more of can be more attributed to chance rather than the intervention that we introduced. Okay, let's look at this from eBay example that we looked at. What they did was they split the audience into two groups, and for one group, the control group, they showed the ads, and for the treatment group, they stopped the search ads. And over time, when they looked at the revenue brought in by both the groups, they both were almost similar to each other, in that the one that received the $50 million in marketing budget produced the same revenue as the group that did not receive the $50 million budget for marketing for the search ads. Using different methods, the researchers attributed that the $50 million did not produce any result in the search revenue. The reason is, when customers search for branded search terms on let's say Google, eBay used to be at the top, but because they were spending that $50 million, that used to take the position of the top search results. The ad used to take the top search result. Instead of clicking the natural search results, customers were just clicking on the ads and they were going to eBay and purchasing. So it was just a wrong attribution by running the search ads, but it was not leading to any additional revenue. And that's how they established the causal relationship between the search ad money spent and the impact on the revenue. Okay, now let's look at the different teams that can use experimentation. There is a common misconception that only customer-facing groups can use experimentation, customer-facing groups like marketing, design, or even the product. But experimentation can be used by any organization, any team in your organization. There are many use cases that all these teams can use, but the most important thing to note is depending on the use case, depending on the systems that you are testing, depending on the impact that you are testing, the experimentation methods and the setups will change. And also we need to take care of all the constraints and factors that we may miss out due to bias. There are many tangible benefits and intangible benefits for an organization by leveraging experimentation. Tangible benefits in terms of monetary value. There are a few large organizations that spend more than hundreds of millions of dollars a year just to set up and run experiments, and their return runs close to $1 billion. But I want to focus more on the intangible benefits here because that's kind of overseen, that's underseen at point. In terms of intangible benefit, the most important one is building a customer knowledge and which compounds over time. We build an unbiased learning about our customers and their behavior, and having more information about our customer helps the organization be agile and move towards customers faster. When we need to take higher complex decisions, it helps in eliminating the doubts around that and builds more confidence before launching it to larger audience. And also by iterating faster, the ideation process in the organization is wrapped up and helps the company to be first to market among its customers, which is very important in this fast world.
Perfect. Thanks, Siva, for introducing such important concepts to us. Next, we're going to move on to statistical background and some overview of different approaches. In the next section, really what you want to take away is an overview of some experimentation methods, drawing a comparison between these methodologies, and then finally looking at a decision-making framework that all of us can go back and apply in our day-to-day, from the next experiment that we plan, basically. Now, I'm going to start here with the first causal inference technique, which is Frequentist. Really what this is okay, I want to preface this section by saying another thing. I want to exemplify a lot of these methodologies more. So I'm going to run through a couple of basic context setting slides a little bit faster. So in case there is any question around a concept that I did not touch upon a little bit deeply, please feel free to drop that question in the chat. Cool. So starting off with Frequentist here, Frequentist is really an approach which looks at probability of an event with relation to how frequently a particular event occurs, right? So it runs across a large number of trials and a large number of data points or instances or observations. Some commonly heard terminologies in Frequentist would be things like confidence interval, p-value, statistical power, and significance, things that you may have come across, in as a part of your day-to-day lives if you are in the field of analytics or data science, or a product manager, or what have you. The essence of Frequentist is that the parameter is a fixed quantity, which means that there is no probability about it. The answers are very binary in nature, which basically means that if a test and control are being compared, the answer is not going to be along the lines of a likelihood of better performance. It's more going to be binary, that this performed better than this, basis the evidence that we received over this time frame that we observed, right? And some industry gold standard techniques are things like A/B tests or ABN tests or multivariate tests. Now let's think about an example here. Let's say that there is a search recommendation engine, which is basically attributing its success to which is basically attributing its success to a metric which is A to C, or add to cart, which is a very common term used in e-commerce businesses. Now, what the team that is deploying the search recommendation engine wants to do is test the differences in how easy it was for customers to discover the products that they were looking for. And now the question thereby becomes that if there is a difference between the conversion rates, as you can see over here between option A and option B on the right-hand side, the first, or the legacy search recommendation engine was reaping a 17% A to C, whereas the new one is reaping a 24% A to C. But the question that we really should ask ourselves is whether this difference is by just pure chance or pure luck, or is this a rare significant result that we should that we can rely our next strategy on. And so initially how A/B tests are set up is that we start with a null hypothesis, which is the H naught that you see on the bottom right of the page. And then we also have an alternate hypothesis. The null hypothesis essentially states that there is no difference in the conversion rates between the two search recommendation engines. That's the baseline. That's where we're starting from, assuming that there is no difference. And what we're really trying to find is evidence for us to refute that baseline understanding that there is no difference, and look for evidence that there may be a difference, and whether it's statistically significant or not. At the end of the experiment, typically you end up with something called a p-value. A p-value is nothing but capturing the difference that there is no statistically significant difference between the test and the control group, right? That there is no statistical difference between A and B, and here is the probability of there being no difference. Inversely, you can look at it as probability 1 minus P would essentially be the probability that there is a difference, right? A couple of more things when we look at A/B tests. What are we trying to do really? We're trying to minimize two errors that one can make while looking at comparing test and control. One is what we call a type 1 error, which is essentially capturing a change through evidence which does not exactly exist, right? Which is something which is also called a false positive. So we want to minimize that. And the second thing that we want to minimize is a type 2 error, which is our test results told us that there was a difference when in fact there was not one. This is called a false negative. I'm sorry, we failed to detect a difference when there actually was one, right? So this is what we call a false negative. And we also want to reduce this. How do we do this? We set this by setting up certain default error rates. The first one is alpha, which is the probability of committing a type 1 error. And the second one is beta, which is a little lesser known, I want to say, relatively speaking to alpha, which is often referred to as statistical power of a test. So when we look at statistical power, what we want to say is that we want to operate with, let's say, a 90% or an 80% statistical power, which basically means that in 80% of the chances when there is a difference, when there is an actual difference, our test will be able to capture it, right? And I'll delve into this a little bit deeper in the later slides. And one of the other things that we have in every experiment are primary metrics, to which we attribute the success or the failure of a test. And then we have secondary metrics for us to be able to comprehensively evaluate, the results of our intervention. Now, diving a little bit deeper into like a p-value. So if I can devote your attention towards the graph on the right, really what I'm trying to showcase here is the difference between the orange colored point and the green colored points, right? And you may see that there's a red point in the middle. So for a one-tailed t-test, for a one-tailed test where we only expect positive results to come out of our intervention, we've set the statistical significance threshold, which is the alpha, to 0.05, right? The difference between the orange and the green point is that the orange point, the orange data point or the orange observation is statistically significant, or what we call a rare result that did not happen by random chance, which is what we can say about the results in the green. So that's the threshold that we've set. And really on a curve of any kind of distribution, what we're looking for is those statistically significant data points. That's truly fundamentally what we're chasing. How do we obtain a p-value? Is essentially at the end of a test, we calculate what is called a test statistic. And there are multiple tests. There are multiple tests on the table for us to, depending on the use case, for us to be able to calculate a test statistic. And then we find the corresponding p-value to that test statistic value to then look at whether our test reaped significant results or not. I was talking about test statistics a little bit earlier on the previous slide. So there are many kind of tests, and really, it comes down to each analyst's personal preference and considerations of the test framework. For example, I typically tend to use Welch's t-test when I'm comparing means in two normally distributed samples. However, a lot of you might see a lot of people using something called a student's t-test, which assumes equal variances between two different samples, which is really a weak kind of foundation to operate basis off of. But to each their own, and there might be contexts where something is more applicable than the other. All these tests, I just wanted to kind of mention here so that there is something for you to take away in terms of what are the things that we should have in our kitty when we're thinking about experimentation. But we're going to touch upon this, in the next time when we meet for the next webinar in this series, when we talk about, from a practitioner's point of view, what is the applicability in which particular use cases for each of these tests, and how do we kind of make that decision. Now, let's talk about some options in the table, right? We start off with a pure A/B test, which is something that I mentioned earlier, where we have one control group and we have one treatment arm. We only have one variant of the intervention that we're making. This could be used for design changes. This could be used for call to action button changes, a bunch of different things. But a classical A/B test typically refers to us having one control and one treatment. On the other hand, a multivariate test is a situation in which we have multiple interventions of different types. A common example is, let's say we have different color schemes for the same call to action, or different positioning of a add to cart button on a given landing page or a given product page. We have different positioning sizes of that, of that button, and we compare those different colors and sizes with the control group to see which particular, like combination of size or color is reaping the best results for us. So that's what a multivariate test is. A switchback test, on the other hand, in switchback testing, the core concept is that we switch back and forth, which is also called intertemporal switching, between control and treatment algorithms in a certain region at alternating time periods. So this is a bias reduction mechanism or a spillover effect reduction mechanism. And we randomize the variant used for each time window rather than simply randomizing the initial variant and flipping back and forth deterministically. So with this approach, each time unit basically is a randomized experimental unit. And maybe that's a little bit of too technical than what we want to get in this presentation here. But what I want to leave you here with is a thought that if you're making like backend algorithm changes for which randomization does not really seem like a plausible way to go ahead with your experiment, then switchback testing is something that could be looked at too. On multi-arm banded, which the philosophy behind this approach is that there's no logical reason to keep sending half the traffic to a version that's garnering 80% of all conversions. Think about this a little bit different. Let's say there's a control and a treatment group. You know that one of those is underperforming relative to the other one. So there is no reason for you to wait out the entire duration of a particular test to kind of see how that performs. If you can determine earlier in that time frame that one is performing better relatively, there is no reason for you to hold back on sending your user traffic towards the better performing variant. So these results in a multi-arm banded test are more of an approximation of what is likely to work rather than an absolute evidence of what has proven to work. So if you're sacrificing some degree of absolute statistical certainty, but you're trading that for a quicker result, right? But if statistical significance means everything to the decision that you're making, then you might want to stay clear of a multi-arm banded test. But this is a very useful technique. It's based on reinforcement learning and reward functions, where you're rewarding a better performing variant by sending more traffic in real time while the experiment is live. The next one that we have here is a sequential test. This is another way of stopping a test earlier, but it's different from a multi-arm banded test. It's not based on reinforcement learning. Sequential tests essentially make decisions during an A/B test by sequentially monitoring the data as it accrues. So it employs something called optional stopping based on what we call error spending functions. So this is a good approach that you could look into if you're operating with univariate hypotheses. But if you're operating with bivariate hypotheses, for example, this gets really complicated really, really fast. And there aren't a lot of good examples for us to kind of learn from, but this is something that we're trying to do with one of our clients, and hopefully there'll be a lot of learnings that come out of that particular exercise that we can share and learn with everybody here on this group today at a later stage in time. The final experimentation method that we have here within this like Frequentist framework is what we call a multi-page funnel test, which is for testing different design philosophies, sales strategies across multiple pages in a given sequence of a user experience. So let's say you don't want to stick to changes that are happening on one particular page, but you want to kind of move through a journey that a user takes when they kind of visit your website, let's say. You can use something called a multi-page funnel test to kind of see how that entire gamut of changes across a journey reap benefits for your business, whatever the outcome variable may be. I want to wrap this section up by talking about Frequentist pros and cons really quick. The pros are that it's available in like a lot of statistic libraries for any programming language. The computation is really, really fast as compared to Bayesian, for example. It's widely applicable and it's easy to ramp up teams to deploy and set up experiments, generally speaking. The cons are that a lot of times the traffic volume that your business or that your particular website or whatever your product or your app, whatever it may be, the traffic volume may not allow for you to run typical Frequentist methodology-based tests. You only estimate the p-value at the end of a test, so you can't what we call data peaking. I want to exemplify what data peaking means. If you divert your attention towards the graph on the bottom here, over the course of an experiment, there are 2-3 data points which are circled in red where we saw that where the p-value came under 0.05, which means that if you looked at the results at day 30 or day 50, or wherever it's highlighted in red, you'll see that you might have had misleading results and informed your business about results which were inaccurate because you did not wait for the entire duration of the test to complete, which is what is needed in like a classical A/B test. So data peaking is not really allowed, and it can reap misleading results for you. Another con of Frequentist approach is that you can't actually know the gain interval of a winning variation, just that it won. So you can't know the actual gain interval of what's the interval, what's the lift really, and what's the range of that lift. Another con is that p-hacking or data dredging, which is selective sampling. Like you bias the results of your test by initially setting up the test for a selective group of people, which is against the true nature of true randomization. So this is something that you can also introduce into your test in error or intentionally, depending on whatever it is. Now, I want to touch upon something a little bit more deeply here, which is one of the criterions for an A/B test. Now, I want to exemplify this through a common example, right? So let's assume that everybody on this call here is working for Uber as an Uber driver. Let's assume, right? All of us are Uber drivers, and we're split into 2 groups, right? Group A and Group B, and all of us drive our Ubers in the city of San Francisco, right? Now, let's say Group A was incentivized to kind of, let's say the incentive was that I'll give you $100. Uber will give Group A $100 for doing, 10 more rides in a given time frame or on a given day. What happens is that because I've incentivized one particular group to kind of be overproductive in chasing that incentive, because we're all operating in the same city, the work available for the other group, which is Group B, naturally becomes lesser. Now, the effect of this is what you can see on the bottom right graph, right? What this means is that what I want to capture, if in ideal conditions, is the green gap, the gap that is shown with the green arrow, which basically means that I want to capture the difference between my group with the intervention and the control group, as the control group may have behaved with no externalities involved. But there is this thing called a spillover effect. What happened here was that the overproductive group is actually cannibalizing the work that is available for the control group to actually do. So what they end up, the curve that they end up seeing on the primary metric that we're evaluating for is this line right here, the bottom line. So what happens is that we end up estimating the effect of our intervention is captured by the red gap here, which is an overestimate of, or an over positive outlook of the effect of our intervention. This is something that we call noise or spillover effect, which is not good for our business, especially if critical decisions need to be made basis the performance of this particular intervention. So this is not a happy outcome. And this is what we call like spillover effects, network effects, noise, incorrect data, overestimation, underestimation, lots of names for basically incorrect, inaccurate results. Now, how do we tackle this, right? We tackle this by something called quasi-experimentation techniques. And what this very simply is in a situation in which randomization is not possible in a given group of, let's say in the city of San Francisco, I cannot logically distinguish or randomize a control group and a treatment group because there will be spillover effects, let's say. We use quasi-experimentation methods, which are useful for estimating the impact of intervention at aggregate levels, right? And we'll get into this on the next slide in terms of what that means. But I want you to stick with that Uber example because I'm going to use that for to explain, quasi-experimentation techniques as well. Some of the pros of quasi-experimentation techniques are that we can gain a high level of evidence without actually randomization. We can choose from a bunch of different techniques depending on the use case that we have and what is feasible for our business to do. And some of the cons are that we cannot truly rule out externalities in quasi-experimentation techniques because what we will be doing is comparing data at an aggregate level, like at a city level, let's say. City of San Francisco is being compared with the city of Houston, let's say, right? So any externalities that occur in San Francisco or Houston will again add noise to our data or our results, but that's one of the cons. And a lot of times choosing an appropriate comparison group or a control group can also present difficulties depending on the scale, size, diversity, and just the nature of the business that we're dealing with, right? Now, what are some techniques? And I know this is a heavy slide, so I apologize for that in advance, but I want you to devote your attention just to the top row here, which is what these techniques are. Now, we used the Uber example, right? The first technique that I want to talk about is differences in differences. Essentially, what we're doing here is, let's say the city of San Francisco is the red line. And we find a comparable control group through, let's say, a principal component analysis or an LDA, and we find a control city. What that control city should be is, it should demonstrate exactly the same trend. The slope should be exactly the same as the treatment city, right? So I go across North America, let's say, and I find that, okay, the city of Chicago is demonstrating an exactly parallel trend as compared to the city of San Francisco. So what difference in differences does is that after the point of intervention, this perpendicular line right here, I see that there is a change in the city of San Francisco's curve on the outcome variable, whatever that may be, right? Now, what I do is I take this difference between these two parallel lines, which is the difference between the city and the treatment and control, and I subtract that from the difference that I see between these two lines after the intervention. So this gap here between the dotted line and this line, this actually is the difference of differences. So that's why this test is called difference in differences, where we attribute the effect of our intervention by subtracting the intervention difference from the post-intervention difference, and thereby finding evidence for the success or failure of our intervention. One of the shortcomings of this test is it relies very heavily on the parallel trend, and if this is not the case, then we can again add noise to our model. Then there's another technique called synthetic control. In a scenario where we can't find one perfect comparable line, we use this technique called synthetic control, which is gaining a lot of popularity in the recent months / 1 or 2 years, where we use multiple control cities. Sticking to that Uber example, we won't try to find a Chicago for a San Francisco, but we will try to find a weighted average of multiple cities to exactly demonstrate that control curve, which is comparable to your treatment group, and which is something what we call a donor pool. And effectively, what we're trying to do is we're trying to create a curve of how the city of San Francisco would have performed if not for the intervention in that same time frame. So this is something which we call it counterfactual, that what would that trend be in the absence of the intervention that we made. Then there are a couple of other techniques called regression discontinuity design, which is basically a pre-test post-test design in which, by setting up a cutoff point, we select subjects. We select subjects just slightly after and slightly before the point of intervention, and compare those groups with each other to attribute the effect of our intervention. And the last one that we have here is called interrupted time series, which is similar to the one that we just discussed, but ITS uses segmented regression to examine the effects of intervention. So again, it requires 2 segments, one before the intervention and one after the intervention, and operates on a single time series data. So that's critical. We need to have a continuous time series data for us to have like strong inferential results. I'm going to move a little bit quicker here for the paucity of time. I think we can skip this question in the interest of time. The next causal inference technique that I want to talk about is called Bayesian. In this inferential technique, it's based out of Bayes' theorem, which is used to update the probability for a hypothesis as more evidence becomes available. And I think an example that I use on the next slide is probably going to make things a little bit more clearer. But what Bayesian inference really does is it derives the posterior probability as a consequence of 2 antecedents, which is a likelihood function and a prior probability, which is what is our historical understanding of the outcome variable that we're operating for. Some commonly heard terminologies are, credible interval, prior, posterior, and the difference from Frequentist here is that the parameter is a random variable, which means that there is no right answer per se, but we operate basis a probability for the hypothesis that we're working towards. Some more differences from Frequentist is it allows us to be more flexible. It allows us to be more flexible. It allows for better uncertainty treatment, and it does not operate basis p-values, which is that we're not looking for statistical significance per se, but we're looking for a likelihood for what is the probability that this intervention that we've made is better or worse or no difference than our legacy or control group. Some benefits of Bayesian are that it works great on small sample sizes, and some of the main disadvantages of this is that it needs like a lot of computational power. And the model fitting procedure is a little bit slower than what it is in Frequentist. So what does this mean, right? I've been talking about probability of hypothesis, probability of evidence. So just very simply put, if you look towards the right here, so probability of the evidence basis a hypothesis is the Frequentist way of looking at things, whereas the probability of looking at hypothesis given evidence is the Bayesian way of looking at things. Here's a simple example. So the probability of someone being pregnant given given that they are a female, is, let's say, about 3%. But the probability of someone being a female, given that they are pregnant, will be much, much greater than 3%. And really therein lies the essence of, what the difference is between frequentist and Bayesian way of looking at things. So we've spoken, I think I've mentioned confidence intervals and credible intervals a little bit, on the previous few slides. Really what this means is that, so frequentist, as the name suggests, it interprets probabilities as the frequencies of that events occurring in the long run. So a simple example is that a fair coin will, show tails half of the time. Hence the probability is half. Bayesian's belief of probabilities are subjective, which is it reflects the degree of belief about events. So our prior belief is that the probability of a coin showing tail is half, right? So that becomes a prior probability, our understanding of how it performs. But when we flip the coin, we keep updating the belief using Bayes' theorem. So in the frequentist framework, the population parameter is fixed but unknown. So a 95% confidence interval basically contains the true value of the parameter 95% of the time. So it will have the true value of the parameter 95% of the time. So that's what a confidence interval represents. Whereas a 95% credible interval for the parameter is a range of values that has the posterior probability of 95%. And really what this means is that the wider the interval, the more uncertainty exists in our posterior. And as the sample size grows, as we feed more data to it, the spread reduces, thereby increasing our confidence into the credible interval that we have. Now, let's quickly compare A/B test and Bayesian, given that we have spoken about everything that we've sort of discussed so far. So let's look at a use case where our objective is to test the efficacy of a new landing page of a website. Simple stuff, everybody does it. Now let's look at the frequentist way of looking at it, right? Let's say the existing conversion rate is 2%, 0.2%. The lift that we expect of the new variant is, let's say, 25%. And the significance level that we're operating with is 5%. We set a statistical power of 80% for this test, which means that 80% of the chance of detecting a change if it exists. After running what we call the power test, the power test tells us that, okay, the person that is running the experiment, you need 220,000 sample size that needs to bypass through our metric, that for me to be able to tell you whether the results are significant or not at 80% power, which basically means that I need my test and control to see 110,000 instances of interaction each before I can actually derive a conclusion of whether my results were meaningful or not. And this may not be possible for a lot of organizations. And and after the conclusion, we do a post-analysis and p-value whether the difference is significant or not. On the other hand, when we look at the Bayesian way of doing the same experiment, we try to find a good prior. But for this example, let's assume that we don't have a good prior at all. Let's say we have no prior information or no understanding about our existing data. And all we have is a very weak beta function, which is the one that you see on the right? Highly uninformative and basically not affecting change on our conclusions. The next step that we do in the process of Bayesian is we select a loss threshold. Let's say for this, we use 0.004%, which is 2% relative loss from our base rate of 0.2% that was discussed right here. Now, after running Monte Carlo simulations, we calculate three main metrics. One is the percentage lift. One is the probability of being the best or better than the other variants. And what is the expected loss? So these are three metrics that we calculate. And over 500 simulations, we see that the variant B was a winner 90% of the time. So if you see this blue line here, that's the variant performing. And if you see the red line here, that's the control group performing. Now, in this experiment, variant B's conversion rate jumped really quickly ahead of variant A's. At each time step, basically, so what you see on the x-axis here is a time step. We calculate the expected loss of a choosing variant A or variant B by numerical integration at each time step. So what we observe is that by the 10,000th observation right here, somewhere around this point right here, what we observed was that by the 10,000th observation for each variant, variant B's expected loss is below the threshold, represented by the black dotted line right here. So this is the threshold that we set here, which is of 0.004%. And what this means is that this would be, relative to the frequentist approach, this would be a huge improvement on the 110,000 instances that we needed to see, as compared to on the 10,000th instance or the time step, we know that variant B is performing better. But this is only like, this is the result of only one simulation, what you see on this graph right here. And over 500 simulations, we were able to say that 90% of the time, variant B was the winner. And 75% of experiments concluded within 50,000 observations, which is 1/4 the requirement that we had for the frequentist methodology. So we need a lot less throughput through our outcome variable to arrive at a confident conclusion. Yeah, so this is and really what the end result of this was, when you have to present it to your stakeholders and when you need to go back to your executive decision makers, the thing that you want to say is that the chance of beating A, or the chance of B beating A, or the likelihood of B beating A is 84%. And typically in business application, anything that has a likelihood of 75% or more is what we typically operate with to say that, okay, the variant won, let's go ahead with it and let's execute that change across the board, depending on whatever your business use case is. Also, if you want to learn more about Bayesian, I would highly recommend reading Andrew Gelman's blogs. Super informative, very, very detailed, and just a great learning resource for Bayesian inferential techniques.
Okay,
I think, yeah.
Yeah, hi Ayush. I think we just have 6 more minutes. So can we like?
I'll just take 2 more. Yeah. Yeah, perfect. So I think the Bayesian pros and cons are kind of already implicitly discussed here, but I want to talk about a couple of things, which is that it allows you to end your tests earlier. It requires a lot less sample size to kind of throughput. It rules out the implementation of false positives, which is a great thing for a business that has high risk interventions. And some cons for Bayesians are that it needs a prior, it needs an informed prior, and it needs a sampling loop, which takes, the computational power needed to run Bayesian experiments and inferences is quite high relative to frequentist. This is a graph that shows data peaking, but I'll skip that just for now because I promised Parul that I'm going to end in 2 minutes, and I'm going to skip this question as well. But think about this. As an audience, think about this, that given all the information here, tomorrow when you go back and try to think about experimentation as a philosophy, are you leaning more towards Bayesian, or are you leaning more towards frequentist, or are we thinking about a hybrid? Because the right one really depends on how you approach your decision making and what the risk at hand is of your intervention. So there is an opportunity for experimentation practitioners to be a hybrid version of all of these methods discussed. I want to end here with the decision-making framework as promised. This basically allows us to really, codify how we think about what is the best use case for our experiments. I'm going to talk about one work stream here before I end and open it up for some questions. Let's say you want to start doing an experiment tomorrow. One of the first questions that you ask yourself should be, can we randomize at a user level, or can we randomize treatment status for a region over time, or can we randomize at an aggregate level, right? Let's say you go with the first one. With the primary metric, the next question that you should ask is, are there network effects? Okay, you don't expect there to be any spillover effects. Great. Do we have more than one test variant? Maybe yes, maybe no, and that would influence whether you go for a multivariate, a multi-unbanded, a sequential, or a pure A/B test, basis feasibility, basis, what are your technical constraints in your organization, such and so on and so forth. the point that I'm really trying to drive here is that when we work with our partner organizations, we leverage similar decision-making frameworks to truly understand what is the best applicable methodology to be deployed for any given use case. And this decision-making framework is not to say that only one approach can be used at a given point in time. I want to end with a thought, which is basically that synthetic control, for example, and differences, these are like what I like to call, and this is not an industry term by any means, these are like hindsight approaches too. So you don't have to kind of set this up ahead of time. You can also look back and see what was the effect of your intervention. So so there's an opportunity for us to kind of go back and evaluate the effects of our intervention, a combination of these tools here, or just one of these tools depending on the use case and how you kind of perform or arrive at a conclusion basis of this framework. Yeah.
I think we just have 2 more minutes left. So very quickly, we'll move to the question. So, you can take up a couple of questions. The first question is, do you know which test ADO target defaults to? So anybody would like to pick this question up?
I'm sorry.
No, this was not the question. I'll reach back to this question came from Melissa. I'll reach back to Melissa with the answer. I want to pick one question that came in from an anonymous person. Others, we know the name, we'll reach back to them with the answers.
How to deal with the experimentation setup is expensive, like each option takes significant effort for applying.
Yes. So generally when we feel that the experimentation setup is expensive, it's basically when we try to set up an experiment where we are testing multiple elements. So what we are seeing companies doing at this point is go back to the drawing board and revisiting the hypothesis and come up with simple ways to test those hypotheses and work on that. I don't know the exact that's being asked here, but in general, it's more in refining the hypothesis that we are testing that will help in reducing the cost or getting answers to the questions that we want.
Okay, great. So can we take one more question, Siva, very quickly?
Yes. Yep.
Yeah. So there's one question. Does cubed experimentation also included in this list?
I think this question came, looking at the time it came when we were discussing about the different types of experiment. Yes, it's part of that. It's more nuanced and a new and a sophisticated method that was brought in here. We are intending to cover this one and the culture around experimentation in our next webinar. So we will go deep into this experimentation method in the next part of the webinar.
Yeah, so I request the audience to stay for 1 more minute, and we have one more interesting question, which is experimentation only relevant to B2C industries? How this can be made applicable to B2B and B2C? Example, digital health, cloud native learning experience platforms, femtech, information services, etc.
Interesting.
No, this is an interesting question. Yes, it's not just relevant to B2C industries. We can use in B2B, B2B, B2C as well, D2C industries too. So the methodologies change, the way we set up experiments and the things that we need to control change. In B2B, the sample sizes, depending on the hypothesis that we are testing, the sample sizes may differ. So we need to look into the particular use case and then look for potential experimentation method that we can use and use that. B2C industry use a lot of A/B testing, but B2 industry in B2B we generally move away from A/B testing and go into other methods.
I think the main difference is that you start dealing with entities and not users. And I think when you deal with entities, there are so many ways that you can think about it, right? Let's say Microsoft is selling Microsoft Office licenses to an organization. Can that be approached from an experimentation point of view, perhaps? But if you're selling Salesforce platform to an organization, right? Can they use experimentation to derive meaningful results? Don't know, right? I think it'll be very use case dependent, and the context really matters here. But I think the short answer is that whatever Siva said, that it depends on the use case and the applicability. Yeah.
Okay, thank you so much, Ayushman, Siva, and everybody who's joined us. If there are any other questions, you can contact us at marketing@facts.com. lifespan.com. You can see at the lower end of the slide. And thank you for joining. Thank you.
Thanks everyone for
Thanks
joining.
all.